Aqueous solutions have an AQ next to them, and aqueous means that it's dissolved in water. So in the top example up there, calcium chloride and silver nitrate are reacting to make calcium nitrate and silver chloride. And notice that all three of the four species up there are AQ. They're dissolved in water. Only silver chloride is not. Now, an interesting thing about ionic compounds dissolved in water is that if they dissolve in water, if they're AQ, they don't stay that way. They actually break up into the ions. So calcium chloride would be calcium 2 plus and 2 chloride ions, stuff like that. Silver nitrate would become silver plus and 2 nitrates. And calcium nitrate above would become calcium ions and 2 nitrate ions. But silver chloride, a solid, does not break up into the ions. And here's what's really important. Solids, liquids, and gases do not break up into ions. And you'd think that would be really relevant, but there's so many AQ things out there that there's going to be a lot of examples with it. So again, anytime you see AQ, you can think about them as breaking up into the ions, but you don't break up solids, liquids, and gases. And we'll come back to this here in a little bit. If you reconsider this reaction, you can break again everything that's AQ up into cations and anions. So the calcium and chloride break up into calcium and 2 chlorides. The 2 silver nitrates break up into 2 silver plus and 2 nitrates. On the product side, the calcium nitrate breaks up into calcium 2 plus and 2 nitrates, but you don't break up solids, liquids, and gases. So AgCl, the 2 AgCl, stays the same. It does not change. And if you look at this equation long enough, notice, for example, how calcium 2 plus is on both sides, calcium 2 plus AQ. And if you look really hard, there's also 2 nitrates on both the reactant and product side. So the calcium and nitrate ions in the chemistry world are called spectator ions. They don't really participate in the chemistry of this reaction. And if you're going to write what's called a net ionic reaction, also known as net ionic equations, you don't want to include the spectators. So in this reaction, what we can do is we're going to literally cross out the spectators. Calcium is the same on both sides. If this was math and you had X on both sides, you'd subtract X and get rid of it. This is chemist's version of that, basically. And also we're going to cancel out the nitrate ions because nitrate is just sitting there not doing anything. So the action of the reaction, which is what I call it, is a net ionic reaction, and it shows the actual chemistry that's happening. So in this example, you'd have 2 chlorides plus 2 silver ions, making 2 silver chlorides. But chemists like to use smallest whole numbers, so let's cut all those 2's out, and the net ionic reaction, chloride plus silver plus, making silver chloride. This is truly what's happening in this reaction. It has nothing to do with calcium or nitrate. It's the silver ions reacting with the chloride ions, making silver chloride. And why this is important, all right, is because maybe we didn't have any calcium chloride available when we were doing this reaction. And we're like, oh, geez, we wanted to make silver chloride so bad. Well, add another source of chloride. Maybe you could add hydrochloric acid, HCl, AQ, or you could add sodium chloride, NaCl, AQ, all right? We really only care about the chloride. We don't care what else is with the chloride, as long as it doesn't make solids, liquids, and gases anyway. The chloride is reacting with silver to make silver chloride. So when you have a reaction that doesn't have any spectators, you can really see what's happening. And in this reaction, it's all about making silver chloride solid, silver chloride as a precipitate. So net ionic reactions do not include spectator ions.
When we put magnesium metal into aqueous hydrochloric acid, the two react. Aqueous magnesium chloride is formed along with gaseous hydrogen.
In this reaction, which is very spectacular, by the way, magnesium metal, it reacts with hydrochloric acid like a lot of metals do. It makes hydrogen gas and magnesium chloride, and it's pretty spectacular. The hydrogen bubbles away and stuff like that. Well, maybe we want to know what the actual action of the reaction is here. Like maybe there are spectator ions, stuff like that. No problem. So if we want to find the net ionic reaction, we're going to break up everything that is AQ. We're not going to break up solids, liquids, and gases. And you should really repeat this with me because it's important. Don't break up solids, liquids, and gases. So what we would do to find the net reaction is we would break up the AQ parts. But again, we're going to leave the solid magnesium alone because it's a solid. And we're also going to leave the H2 gas alone. So if you break up the HCl, you've got 2H plus and 2Cl minus. We'll also break up the magnesium chloride. That makes magnesium 2 plus and 2 chlorides. And when you look at this reaction, which sometimes I call the total ionic equation, you want to find chemical species which are both reactants and products. And sure enough, you can probably see here, chloride is on both sides. So if something's on both sides, it's called a spectator ion. And you don't want to include spectator ions in the net ionic reaction. So let's pull the 2 chlorides out and just show what's left. The overall net ionic equation here, magnesium metal, magnesium is a solid, reacting with 2H plus aqueous to make H2 gas and magnesium 2 plus. So chloride is a spectator. And if, for example, when we did this reaction, we ran out of hydrochloric acid and we're like, oh, darn it, we could have used nitric acid instead. Nitrate would have been a spectator instead of chloride. Or maybe we could have used hydrobromic acid, HBr. Bromide would be a spectator. So this really does show what's happening in a chemical reaction, and it can be kind of a cool thing for a chemist.
A solution of lead nitrate is added to a solution of potassium chromate. A yellow precipitate of lead chromate forms, leaving potassium nitrate in solution. The potassium and nitrate ions do not take an active part in the reaction.
Lead 2 chromate is a very cool yellow color. In a lab in Chem 223, if you take it with me, I'll show you what it actually looks like in the lab. It's pretty spectacular. But anyway, to make it, in this case, we're adding potassium chromate and lead 2 nitrate together to make lead 2 chromate, a precipitate, a solid, and 2 potassium nitrates. Well, when you do the net ionic analysis on this, and I encourage you to try this just to make sure you're good, both potassium ions and nitrate ions are spectators. So when you pull them out, lead 2 plus aqueous plus the chromate ion aqueous makes lead 2 chromate solid. There's a handout on net ionic reactions. If you'd like to check it out, it'll have more information on this. We'll also do a lab on net ionic reactions coming up too. Here's a reaction. Potassium hydroxide is reacting with iron 2 chloride. It's going to make iron 2 hydroxide and potassium chloride. And the question is here, what is or are the spectator ions in this reaction? Well, you could break it up into the ions, break up all the AQ things and cancel what's left and stuff like that. Another way, though, to think about it, you don't want to eliminate anything that makes the solids, liquids, and gases. And iron 2 hydroxide is the only solid here, solid, liquid, and gas. So anything that goes into that is going to be part of the net ionic reaction. And what I mean by that, the iron 2 plus and iron 2 chloride is going to be useful. And we're also going to need the 2 hydroxides in potassium hydroxide. The hydroxides and the irons will make the iron 2 hydroxide. So the spectators are going to be basically the parts that I didn't underline. That's going to be the potassium right there, and that's going to be the chloride too. And another way to see it, you can see that both potassium and chloride are in aqueous potassium chloride on the product side. So for all of those reasons, hopefully you can see that the potassium ion and chloride ion are going to be the spectators in this reaction, and they're not participating. So again, if you didn't have KOH in the lab at that time, maybe you could use NaOH or LiOH. You'd have a different spectator, but the same chemical reaction would occur. So chemists like to classify chemical reactions according to what they'll do. And a precipitate reaction or a precipitation reaction is just a reaction where a solid forms. And to understand when compounds form solids and when they don't, at this level we'll use what a lot of chemists use, which is called a solubility table. And a solubility table just shows different combinations of chemicals that can result in a soluble or insoluble products. Now, soluble means no solid. Soluble means everything is aqueous, it dissolves. But insoluble means that a solid is going to form. So if you see a precipitate form, that means you have something which is insoluble. insoluble. And that helps you to figure out what the action of the reaction is, stuff like that. Now, the textbook uses a solubility table that looks like that one there in the picture, and that's fine. It's okay. However, I would like you to use a different version, and I'll show that to you here in just a second. For Chemistry 221 through Chemistry 223, this is the solubility table I'd like you to use. And it's not too difficult to figure out if you just spend a little bit of time of it. So first of all, notice in the upper left-hand corner, it says soluble compounds, all right? And it lists a whole bunch of different variations, but some of them have exceptions. So if you have, for example, a salt with sodium up there, salts are just ionic compounds, by the way. Sodium nitrate, sodium acetate, sodium blah, 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 something you don't recognize, all right? Anything with sodium, as far as we're concerned in this table, is going to be soluble. So one day, if you're researching at a high-level research lab and you show me this chemical you made and you call it sodium blah, 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 and I have no idea what blah, blah, blah is because, I haven't studied this kind of stuff before, no worries. Sodium is enough to say this should dissolve in water because there's no exceptions over there. And notice that sodium, potassium, ammonium, nitrate, chlorate, perchlorate, acetate, all of these, as far as we're concerned right now, have no exceptions. So they're always going to be AQ. They're going to be soluble. So another compound you're making is blah, 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 acetate. And again, I have no idea what that first part is. Acetate is enough to make it AQ. I'd like to highlight here the chloride, bromide, and iodide salts. Those are going to be really important to us this year. Those three are usually AQ, usually soluble, but there are some exceptions. The silver plus, mercury 2,2 plus, and lead 2 plus ions. Those three ions are called the group 1A cations, and we'll do a lab about this in Chem 223. But when those three are with those chloride, bromide, and iodides, they will make an insoluble compound. But again, most of the time, chloride, bromide, and iodide are insoluble. Now on the bottom, we have compounds which are mostly insoluble with a few exceptions. So carbonate, phosphate, oxalate, chromate, sulfides, hydroxides, oxides, all those things, always insoluble unless they're with ammonium and the alkali metals. And alkali metals are sodium, potassium, lithium, all right, cesium, francium. You don't see those very often, but those would be included in that. So anything with ammonium, sodium, potassium, etc. is going to be AQ, but almost all the rest of them are not soluble, and you'd write an S to it. So on the right-hand side, I have kind of an example. I'd like you to tell me if these barium compounds are soluble or insoluble. And the first one is barium nitrate. Well, nitrate, as you can see, nitrate is one of the ones always soluble. And so there's no exceptions to that. So anything with nitrate should be AQ. It's going to be soluble. So BaNO3,2AQ would be the right way to write it. Now, BaCl2 has chloride, and most of the time, chloride is soluble, AQ, with three exceptions, silver, mercury, and lead. Well, barium is not one of those three, so we would say that it's soluble, and we should write BaCl2, AQ. It dissolves in water. However, if I asked you about barium sulfate, all right, sulfate's down here at the bottom. It's usually soluble, but there are some exceptions. And when you look over there, notice that barium is one of the exceptions. So BaSO4 is insoluble. It is not soluble. We should write it as BaSO4 solid, okay? So this is how it works. It's not too sophisticated. We will see in Chemistry 223 that there are some better ways to figure out when things are soluble or not. But overall, this works pretty well. If I'm asked by somebody in the hallway of my office, near my office, like if this compound is soluble, I will think back to this list and it'll give me a good answer. I can do a better answer, as we'll see if you have Google and a calculator with you. However, if you're just kind of talking and walking with someone, this is kind of a nice way to make it look like you're cool and be able to predict solubility. The solubility guide can also be found in several labs we're going to do. It is available online at mhchem.org/SOL. So if you go to that website, you'll see the solubility guide and no problem. There are a couple of ions you should just know that are always going to be AQ. Sodium, potassium, lithium, ammonium, nitrate. Those 5 especially. If you know chlorate and all those things, that's great. Now, most of the time, sulfate is soluble, but barium sulfate's one we'll see a lot. Chloride, bromide, and iodide usually soluble, but when they're with silver, mercury, and lead, that can be a little weird and they can make insoluble compounds. And we'll see that coming up here too. Okay, so here's a question you might see. It says, which of the following is the only insoluble salt in water? And there's lots of different pieces to it. Now, I don't expect you to memorize that chart. However, I think it's very helpful if you know the ions, which are always AQ. So what I mean by that, nitrate is definitely one that's always AQ. So there's no question that's going to be soluble. Sodium, always AQ. Potassium, always AQ. Lithium is an alkali metal, always AQ. Chloride is only insoluble with silver, lead, and mercury, so that's not a problem. But speaking of silver, lead, and mercury, here's iodide in C. Now, iodide is usually AQ, but it's not when it's with silver, mercury 2+, and lead 2+. So answer C here is going to be the insoluble one. So if you can answer questions to that level, like if you know the ones that are always soluble, you know the chloride, bromide, and iodide exceptions, and also remember barium sulfate's insoluble, you should be pretty good to go in this class.
Potassium permanganate is an ionic compound. It dissolves readily when mixed with water. Dissolution involves the breaking of the bonds that hold the compound together. The ions become distributed throughout the water, forming a solution. Water molecules are made of hydrogen and oxygen. The hydrogen side of the molecule has a positive charge. The oxygen side is negative. When water molecules contact an ionic compound, such as potassium permanganate, their positive sides are attracted to the negative ions of the compound, and the negative sides of the H2O are attracted to the positive ions in the compound. These attractions allow the crystal lattice to break down, and the compound dissolves.
We saw as a Lewis structure that water is polar. It has a slightly negative side by the oxygen, and it has a slightly positive side by the 2 hydrogens. And water uses this polarity to dissolve ionic compounds amazingly well. So potassium permanganate, which is actually a solid when you first put it in water, the potassium permanganate breaks up. So it breaks up into K+, and the permanganate ion, MnO4-. And how it does it, the K+ is surrounded by the negative side of water. So the middle part, the oxygen, the tip of the V, if you will, that's the negative part of oxygen, and it surrounds the positive potassium, and it pulls the K+ from the KMnO4. And likewise, the permanganate, the MnO4- ones, which are negative, they're surrounded by the positive part of the hydrogens, the middle of the V, if you will, of water, and it surrounds it and pulls it away from the ionic lattice. Pretty amazing. So water is fantastic in the way it can get it around. Potassium permanganate is a real beautiful purple color. If you ever get a chance to see it, it's pretty spectacular, like a lot of the inorganic compounds. But this is why water is so great about dissolving compounds, and it's what allows a lot of life processes to happen.